This question is to conduct a chi-square goodness of fit test to determine if a calculator simulation of a six-sided die. A statistics teacher used a calculator to simulate rolling a fair six-sided die 96 times. The outcomes were saved in a list, sorted, and tallied into a frequency table. The results showed that phase 1 occurred 19 times, phase 2 occurred 15 times, phase 3 occurred 10 times, phase 4 occurred 14 times, phase 5 occurred 17 times, and phase 6 occurred 21 times. Based on this data, does it seem like the calculator simulation represents a fair die, or should we suspect that something is off? Step 1. State the hypotheses. We are testing whether all 6 sides of the die are equally likely. The null hypothesis is that the probability of each face showing up is the same, which means the probability of face 1 equals the probability of face 2 equals the probability of face 3, and so on, and each is equal to 1 divided by 6. The alternative hypothesis is that at least one of those probabilities is not equal to 1 divided by 6. Step 2. Decide on the test. Because we are comparing observed counts to expected counts across categories, this is a classic case for a chi-square goodness of fit test. This test helps us determine whether the differences we see between observed and expected frequencies are large enough to be considered statistically significant. Step 3. Find the expected counts. Since the die is assumed to be fair under the null hypothesis, we would expect each face to appear equally often. So, we take 1 divided by 6 and multiply it by 96. That gives us 16 as the expected count for each face. Step 4. Calculate the chi-square statistic. Now we compare observed counts to expected counts. For each face, we take the difference between the observed count and the expected count, square that difference, then divide the result by the expected count. We do this for each of the 6 faces, then we add those 6 results together to get our chi-square statistic. For face 1, the observed was 19, expected was 16, so the contribution to the statistic is 0.5625. For phase 2, it was 0.0625. For phase 3, it was 2.25. For phase 4, it was 0.25. For phase 5, it was again 0.0625. And for phase 6, it was 1.5625. Add all those up and you get a total chi-square statistic of 4.75. Step 5. Determine degrees of freedom and p-value. The degrees of freedom is equal to the number of categories minus 1, which is 6 minus 1, giving us 5 degrees of freedom. Using a calculator or chi-square distribution table, we find that a chi-square statistic of